Today we're going to fix the runout in this 5C Speed-Collet chuck. We'll try the easiest things first, but you know how things tend to escalate around here. Welcome back to Cloud42, I'm James. You will remember in a couple of previous videos I cleaned up a Hardinge-Sjogren 5C Speed-Collet chuck and made an adapter to install it on my lathe. You'll also remember that the runout once it was mounted was pretty disappointing. Well, today we're going to dig in, see if we can figure out what's going on, and do whatever it takes to fix it. Before I try to fix anything, I want to take some measurements and make sure that I understand exactly what I'm dealing with. The right solution to this problem kind of depends on where the error is coming from. So I've got a 3/4 inch collet and a 3/4 inch gauge pin in here. We'll put an indicator on it and just see exactly what we've got in terms of total indicated runout. Now that looks like about 3 thou, and I've taken this chuck off the lathe and put it back on several times, and it's always around 3/1000ths of an inch. So if we just let this spin on its own to make sure that I'm not influencing it by pulling on it and flexing the lathe, we're going from just under 0 to just under 3. If I bring this back around so that it's peaking at 0, then we can clock this around and try to figure out exactly where the high and low spots are. So that's right at 0. I'll mark that on the chuck. And in fact, I'm going to be handling this a lot, so we'll use tape to make sure that I don't end up just rubbing the marks off. So this is the 0 point. And if we rotate around, the high spot is not unexpectedly just about opposite that. So we'll put a piece of tape on here and we'll mark this as -3 thou. Here between those two marks on this side, we're at about -1. And on the other side, it looks like we're right around -2. So that gives us an idea of where the high and low spots are. So as we fiddle with this, we can see if those are moving. Now I want to make sure I know how this is clocked. There's 3 screws in the back here that are holding this in place, and I'm going to go ahead and mark those because I want to rotate this into all 3 different positions and see if the high and low spots move, just to try to understand better what might be causing the runout. So I'll put a single punch mark here on the chuck. It's not very deep, so I'll hit it a couple of times. And then I'll put a single mark next to this screw. Again, hit that multiple times. Then we'll go around to the next screw and I'll put 2 marks here. Just double hitting all of these to make sure they're nice and pronounced. And then we'll put 3 marks next to the 3rd screw. 1, 2, and 3. That way when we take this off and put it back on, we can tell what position we're actually putting it in, and we can see if there's any difference between the different mounting positions. As long as I'm taking this off, I have to take these locks off. Let's go ahead and pull those out and then throw an indicator back on it and just make sure that the little clamp locks weren't influencing the position. It looks like we've got the same 3 thou of run out. So that doesn't appear to have been making any difference. Use the spindle lock that we made in a previous video to hold this still, and then I'll grab a strap clamp and pull this off. Unlike the chucks that have jaws where you can just throw a crescent wrench onto one of the jaws, there's nothing here to grab, so strap wrench is the easiest way to get this loose. And it turns out it's heavy. And when it knocks your hands against the ways of the lathe, it hurts. The first thing I want to do is just pull this adapter that we made off of the chuck and check it just to make sure there isn't something crazy going on where it got warped or I mismachined it, or maybe it doesn't seat the same on the lathe every time we put it on. So I'll just pull these 3 7/16 20 screws out of the back and we'll pull it off. And you'll remember from when I made this, the taper is a little bit on the tight side, so releasing it takes a few taps. And this was one of the speculations that I got in the comments, is that that's too tight and that might be the source of the runout. And we'll see. Put that back on, spin it down till it bottoms, and then we'll just go ahead and take the strap wrench and make sure that it's really firm, and it is. It doesn't move at all. Then we'll bring out the indicator and check the taper. See how we're doing. And that doesn't look like there's much, if anything, there. Yeah, I think all you're seeing there is the spiral tool path from turning it. Moving the cross slide back and forth just to show that the dial indicator is live, and yeah, there's essentially no run out there. Bring it all the way up close to the shoulder. And we've got the same thing, no run out. Let's check the face just to make sure this isn't some kind of a weird angular thing there. That looks pretty good. I'll move the cross slide in and out. There's just barely a little band that goes between the screw holes and the flats, and sure enough, we're seeing the same spiral tool path that the tip of the indicator is skipping over. Other than that, it is dead straight. So it doesn't look like there's an issue with the adapter. Let's go put this back on the chuck and try it in some other positions. We took all of our initial measurements with this single punch mark lined up with the punch mark in the chuck. So we'll move this around and rotate it so that the 2 punches are next to the mark. Put the screws back in and tighten this down. Now, I did see some call in the comments to use a torque wrench. If we see some variance between having this in different positions, it might be worth going back and doing that. But I'm using the impact wrench set to the same setting, running it about the same amount of time on all 3 screws, so they should all be about the same. And we'll see what the actual run out measurements look like. And again, if nothing is changing through moving this around, then I think we can be pretty confident that that's not the issue. If we take it on and off and on and off and see the same thing no matter what. Here we got our high spot. There's -1. There's -3 about. There's -2 and back to 0. So we've got our same 3 thou of run out. And the measurements are all the same in all the same positions. So rotating the chuck 120 degrees on the back adapter plate doesn't appear to have made any difference. Let's pull it off, switch it around, and put it in the 3rd position that we haven't tested yet. Rotate it around so that the 3 punch marks are next to the screw that we marked, and run it all back in. Now you'll note that the material in the backing plate is 2-way symmetric and the chuck is 3-way symmetric. So if there was some kind of distortion happening, we would expect that to change as that back plate is rotated around. But there's 0, there's -1, there's -3, and there's -2. So rotating that backing plate around on the chuck does not appear to make any difference. So I'm pretty sure that the interaction between the backing plate and the chuck is not the issue. The backing plate is running concentric, and the chuck mounted in 3 different positions is all coming up exactly the same. So I don't think that's the issue. And I would think if it was a torque issue on the screws, then taking it off, putting it back on, tightening the screws in a different order, we would see some kind of a change, and we're just not. Let's make sure we don't have something weird going on with the collet. I'll take out the 3/4 inch collet. I'll put back a 1/2 inch collet with a 1/2 inch pin. It's a cheap import collet set. Let's see if that makes a difference. Get this run in so it's peaking at 0. It's about the same 3 thou, maybe slightly more. I guess we're a little bit under 0. There's a little bit under -1, a little bit under 3, and a little bit under -2. So no, it's not the collet or the pin, because we're getting exactly the same result with a different collet and a different pin. Let's actually check the taper. This is a little bit gnarly, it's a little bit bumpy, but as long as I'm measuring the inside of the back, then the offset should be in the same direction. And we got some cosine error because it's at a different angle, but this should at least give us some kind of an indication. So there's -3, that's the low point. There's -2, right about there. There's our 0 mark. And there's -1. So it looks like all of the error is actually in the taper of the collet chuck. So I think we've ruled out the collet. I think we've more or less ruled out the backing plate. So the error does appear to be in the chuck itself. This collet chuck is made in two halves. There's a body on the back and a body on the front, and they're sandwiched together on two pins that go through the planet gears. And you'll remember when I cleaned this up, I did take it apart and I did not keep track of which way it went back together. There's two ways it could go back together. I put it back together. I might not have gotten it in the same position it was in from the factory, hence the position it would have been ground in at the factory. So let's take this apart and try switching it back around. I really don't want to lose the gears. I don't want to retime everything, so I'm doing this really carefully. I just loosen the screws a little bit and then press down on the screw heads. We should be able to break it free. And there it is. So now I can take the screws out and try to lift this off without disrupting anything. There's a thrust bearing in here. There are the planet gears and the outer ring, and I really don't want to disturb it. Let's see if we can get this off without disturbing anything. And I know you were hoping everything would fly, but it looks like I got it off. So let's rotate this around 180 degrees and put it back together. Again, I didn't see any markings that I could follow when I put it back together when I cleaned it up, so this is just trial and error, and we'll just see what happens. But the error does appear to be between the mounting taper, which is in the back body of the chuck, and at least the collet taper in the front, which is in the front body. So it stands to reason if there's some kind of imperfection in how those pins line up, this could be a source of error. So let's put this back together, torque everything down, and then go remeasure and see if it made any difference. And as far as how this goes on, I'll go ahead and just put it back in position 1. We've already ruled out the position of the adapter as having any kind of effect. So we'll just run it down, run the screws down exactly the same as we have on all the other tests, and go put this back on the lathe. It's nice and free. I think we got it on straight. And back to the lathe, we repeat the same drill again. If you can hear me sighing in the background, it's because I'm getting tired of putting this chuck on and off the lathe. Now that's different. What have we got there? About a thou and a half of run out, maybe a little bit more. It's hard to tell with the angle here. So I think we've cut the total indicated run out there in half. So some of that error was from misalignment of the front and back of this chuck. Well, that's an improvement. It's not all the error, but it's a lot of it. So there's 0. It's kind of close to our 0 position. It's not exactly lined up with it. And there's -1. But there's -3, and we're back to -1. And there's what I had marked as -2, and that's up at 0. So yeah, it's not a direct one-to-one error change. It's certainly the axis that this moved is not the same as the axis that it was offset. So that was part of the error, but not all of it. Well, since the front and back of this collet chuck are two different pieces, now I'm wondering if I can tap it and adjust it. So I'm just going to loosen these screws a little bit. Just using a piece of brass here, a piece of copper, little copper knocker that I have that I use over on the mill to seat things in the vise. And I'm going around and just loosening each of these screws, breaking it loose and then bottoming it back so that it's firm but not tight. You'll put the dial indicator back on it and tap the high spot, not on the pin, but on the body of the chuck, just to see if we can move it. And that did not move. That's about the high spot there. Little tap. Still didn't move. A little harder. And yeah, this isn't moving. So it is tight on the pins. I'll go ahead and snug these back down. Try reseating the pin and the collet just to make sure that nothing is changing here, that any of the variables that we can control that are separate from what we're testing, we can fiddle with them and they repeat. And this appears to repeat. Let me grab a tenths indicator here just because we're getting down into the noise on that thousandths indicator. And let's see what we can see. What do we actually have here? moving the cross slide around and getting this lined up so it peaks at 0 is actually a lot harder than it looks. So it looks like we've got about 1/10. That's pretty close, but we know that the taper in this thing is gnarly and most of that error is in the taper, at least it matched up before. I think it might be worth trying to grind out that last 1/10. There's not a lot there, and if it turns out that was a mistake and we find some other kind of a problem later, 1/10 is not much, and we can grind it back in again if we need to. There's plenty of material. I'm going to grind the taper using the compound on the lathe. And to get the compound set to the right angle, we have a couple of options. We could look up the spec in the book, which is 10 degrees on each side, and we could get out an angle block and set the compound to exactly 10 degrees. But not all 5C collet chucks are ground to 10 degrees. Some of them are at a little bit different angle to compensate for the way the collet collapses when you clamp something. It's undersized to make sure that it has the right kind of bearing. It wasn't totally clear to me. There wasn't a lot of consensus that I could find on exactly what it should be. So I figured the best thing to do here is just to match the taper that's already in here. So I've got a dial indicator mounted on the compound, and I'm running the compound back and forth, and I'm just adjusting the compound until the dial indicator doesn't move, meaning we've matched the existing angle on the taper. You have to be very careful to make sure that the indicator is on center height in order for this to work properly. But I'm seeing essentially 0 movement now, so we'll snug down all 6 of the studs on here. And that looks pretty good. Now the inside of this taper is a little bit chewy, but I'm happy with that. I think that's about as good as we're going to get with this kind of a setup. Now to actually grind this, I'm going to use the best spindle that I have in the shop that can run at a suitable speed with a small enough stone, and that is my NSK pencil grinder. So I designed and 3D printed a clamp to hold the pencil grinder handpiece so that we can do the grinding. This is just a part. This is just printed in carbon fiber reinforced PLA, and it's sized exactly to fit this on a couple of the different diameters. Goes in here, tighten down the 3 screws, and it should be rigid enough to do the grinding. Now the PLA is a little bit flexible, something metal might be better, but the pressures on this are going to be so small, I'm not expecting any trouble. The wheel I'm using here is a Dremel stone. This is a 1/2 inch diameter aluminum oxide wheel, and that's all I know, except that it has a maximum RPM of 25,000, so we'll stay under that. I don't know the grit, I don't know the hardness, they just don't publish any of that data. I do know that I don't trust it, so we're going to start by dressing it. Got a single point diamond on a magnetic holder here at about the center line, and we'll just go back and forth and dress it. Now I didn't think about it when I started here, but dressing on this side of the stone means that I'm trusting that the spindle is exactly parallel to the movement of the compound, which I can't guarantee. So we really need to dress the wheel on the side we're going to grind with, which is the near side. And the other advantage you have of grinding on this side of the stone is that it throws all the grit right up into your face. This isn't a super rigid setup. I'm not super happy with this particular dress, but it looks okay. We'll try it. Just so I can see what I'm doing, I'm going to blue up the inside of the taper here with some Sharpie. That way I can tell where I've ground and where I've not. And if I've got high and low spots, I can see where those are. And just give me a visual indication of what is happening. Get that nice and blue. We'll spin up the wheel, 23,000, 20,000 RPM, and bring it out and touch it off. Then we'll bring it out, feed in maybe 1/10. And just start feeding and start grinding. Now I want to take this super slow because I don't know how this is going to behave. I don't know really how this spindle is going to behave under load. I don't know how this stone is going to behave. I don't know anything about the material here. So I'm just making pass after pass, going maybe 1/10 at a time and going nice and slow. And you can definitely hear it bogging down and changing the speed of the spindle. It's not ideal, but I am making progress, and hopefully we'll get this thing to smooth out at the end. Speeding things up seems to help a little bit, but this is super slow going. What you're seeing here is about 30 minutes of grinding because I just did not want to push this and break anything or jam anything. And you can see that as I get deeper, it's really bogging down. I think grinding on the full face of the wheel is just not a good idea. So what I'm going to do is I'm going to angle this ever so slightly so we're grinding on the leading edge of the wheel. And that took a bunch of the load off of the spindle and made this go a lot more easily. So we're just grinding on the front corner, and of course that front corner is going to slowly break down. So as we feed in, the actual grinding point's getting a little bit wider. And as you can see at the outer side of the taper, we've got this thing all the way down to clean material and we're through all the damage. But it still doesn't sound great in the back. But we've got a significant portion of the taper that's clean now. So I think I am going to call that good. I don't want to overcut. Let's just do some testing and see where we are in terms of concentricity now. We can always take more, but we can't put it back. Here's the same 3/4 inch collet and pin that we tested with earlier. We'll go ahead and chuck this back up and see if we have made any difference. Certainly hope we've done something. Put the indicator back in the same position here. Get close to 0 and just see what we've got. And that's better, but it's not a ton better. We're a little under a thou here maybe. Yeah, maybe 8/10, down from 12/10. So we've definitely made a difference. It's a little bit more, a little bit further out on the pin. That's to be expected because we're not grinding the inside register where the back of the collet fits. It's kind of a limitation on what we can do here, but we've made an improvement. It's not great. Let's take a look and see how the taper actually turned out. Make sure we really are grinding it true. And there on the outer side of the taper, that looks pretty good. We get deeper in the taper though. There's definitely some garbage in there, and exactly how much depends on exactly where we put the point of the indicator, because there is some wear back there and we never did get that all ground out. So the real interesting question is exactly where the collet is riding. And I guess because we were grinding on the outside first, even though we tried to match the angle of what was already there, I'm not sure I can totally explain that unless I didn't get a very good match or unless something moved. But out here on the point, this is concentric. And that looks really good. So maybe we just need to continue grinding. If we take a little closer look at the grind job here, we can see a couple of things. One is that the surface finish on that is fine, but not great. The other thing we can see is there is still quite a bit of damage back in there. There's some sort of intermittent damage, and there's some damage where the splits in the collet are, so that when you compress down a 5C collet, it rides kind of on the 6 points of the corners of the 3 parts of the collet. So I'd kind of like to find out, are we hitting in those damaged spots or are we hitting on the freshly ground sections? So I'll blue that up, put a collet in there, we'll clamp it down and just see where the blue is disturbed so we can see where the collet's riding and figure out if it's riding in the damaged areas or if it's riding in the clean areas that we just ground. We'll clamp and unclamp this a few times just to get it to rub. And where is the wear? Where is it hitting? And it's hitting in the back where all that damage is. Yeah, that is not ideal. So essentially we haven't ground out the damage in the areas that the collet's actually riding on, which is why we're still seeing the error in the motion at the end of the collet. But before we go any further, let's see what angle we're actually at here. I've got a 10-degree angle block here, so this should be exactly the taper on the collet. And we'll throw a dial indicator on this, move back and forth, and just try to see, are we at 10 degrees? I think we're a little bell-mouthed based on how I see this running in the actual taper and where the blue is hitting, and sure enough, we're actually bell-mouthed. From what I'm reading, I think you actually want this exactly the opposite. Instead of being slightly over 10 degrees, you want it slightly under 10 degrees, so even as the collet collapses, it still tends to clamp on the end of the taper. But I'd be satisfied for just matching it, so I'll tap this around till we're at exactly 10 degrees, and then we'll go back to grinding and we'll get it ground in nice and clean to 10 degrees, see how it functions, and see where we are. we have to go at least that far to clean it up, and we can always go a little bit further if we want to adjust the angle in the other direction later. Since we're just grinding on the end of the stone, I went ahead and just dressed this by hand with a cluster diamond like I would on a bench grinder, and went back to grinding with all the glazing removed from the wheel. And it's cutting a lot better starting out this way and not letting the thing get glazed up in the first place. And as you can see, we've already made some progress. We're contacting in the back of the taper, which is exactly what we expect. And I just went back and forth, taking again 1/10 at a time or so, 2/10 or so off of the diameter, until we got to the point where it was running nice and clean all the way through. And you can still hear some pulsating in the back, so there is a little bit of imperfection or a little bit of out of concentricity in the back. And I just went until that was really minimized and went back and forth and let it spark out. You can still hear some variance back there, but I think it remains to be seen how much that'll actually show up on an indicator. All in all, between both grinding sessions, I fed in about 2.5 thou on the diameter. So when you figure that the stone was probably breaking down, we probably took between 1 thou and 1.5 thou of material out of the bore. So it was really minimal. It was really just enough to clean this thing up. And clean it up it did. I am really liking that grind. That fish scale is all gone. Having a nice clean wheel and going a little quicker seems to have worked better. Just remains to be seen what happens when we measure it. Got the thousandths indicator back out, and we'll reach as far back in on this taper as we dare and see how we're running. That looks a lot better. The needle's moving. It might be 1/10, might be 2/10. Out here on the tip, that looks really clean. I see basically no movement at all. I might be able to see my own breathing in the needle. But we get back in the back third of this, and that is a ton better. So back where that collet was riding previously, we're not sure it's still going to be riding there, probably not. But this looks much, much cleaner. So let's get a collet and see what kind of difference we made. And we've still got some movement there. How much is it? I don't know. Maybe 8/10, maybe a little bit less. It's really hard to read on this dial indicator. Let's bring out the tenths indicator and see what it actually is. Oh, and that's good. What is that? 4/10, 5/10, something like that, right up next to the end of the collet. That's more like it. Now we're getting into the range of what the error might be on these import collets. If we move out to the end, there's a little bit more. What is that? 1.2, 1.3 thou, so 13/10. And that's because the axis of rotation of the pin is not directly in line with the spindle. Now we can grind the nose taper on the collet chuck, but we can't do anything about the way the back side of that collet is seating back inside the chuck. There's a register back there. It gets influenced by the threads. It kind of is what it is. And unless you want to regrind the mounting taper to move the whole chuck body around, it's hard to really do much about that. Blew this up again and just see where the collet is hitting and see if we did manage to move that contact point forward. And I can already see the blue on the collet, and it looks like we're pretty much in the middle of the taper. That's what I was hoping for, and if we look inside, the story is the same. We're no longer riding on the back of the taper because we've matched the 10-degree angle of the collet pretty much exactly. So it looks like we are riding further out on the taper. I might like to see this ground so it's contacting a little bit further towards the front, but this should be just fine. And the surface finish in there looks really good too. I would be proud of that under pretty much any circumstances. Now, we might want to try taking a little bit further so that the angle's less than 10 degrees so that it contacts further out on the point. Based on some recommendations I saw online, do we want to spend more time on this? We could. It would be interesting. I think I'm going to stop right there. The taper is running true at this point, though there is still some remaining error. It's probably coming from a combination of the import collet that I'm using and the seat for the other end of the collet back inside the chuck. It is way better than it was, and my plan is to just use it at this point. If I decide later that I want to put more time into it, it ought to be possible to mount the whole chuck on a mandrel, put it between centers, and regrind the D13 mounting surfaces. Though that seems like it would take a lot of work and require a lot of faith in the collet. Feel free to let me know down in the comments if you've ever attempted anything like that and how it went. The 3D model for the NSK grinder tool holder is available on Patreon, along with the files for all of my other projects. And if you're already a patron, thank you. Your support makes this possible. Thank you for watching.